So hello friends, we'll go through the design of shafts today. So it consists of what is the meaning of torsion of shafts, design for strength and design for rigidity. So with steady loading and ASME and BIS codes for power transmission shafting, shafts under fluctuating loads and combined loads. Okay. So before I want to start this one, let us notify what is the meaning of shaft here. Okay. So what is the meaning of shaft? So shaft is usually refers to an machine member, so which is used to transmit the power from one position to the other position. Okay, so with the help of some gears, with the help of some pulleys, and with the help of some sprockets, so where you can transmit the power from one position to another position, right? So now the shafts are basically classified as two members here. So one is our rotating shafts, another one is stationary shafts, okay. So actually, so if you consider technical term, these rotating shafts are used to transmit the power. Okay, they are used to transmit the power. Okay? So again, stationary is what it is called as an axle. Okay, so which is called as an axle, so which is going to support the only load. Is going to support only load. Okay, support the load. Okay, so the load may be of an impact, or maybe stationary, or maybe sudden. Okay, or maybe sudden. So rotating shafts are used to transmit the power. You can call them as a transmission shafts. Transmission shafts, where you are going to use these as power transmission. Okay, again, so based on the length, okay, based on the application, as well as based on the position, you can classify the transmission shafts as a spindle. So you can classify it as a spindle. Okay, so next one is what a counter shaft. So next is what a jack shaft. Okay. So last one is what a line shaft. Okay. So spindle is what originally in small length. It is of a small length which is used to transmit the power. Okay, which is used to transmit the power. Okay, so normally it is a taper. Okay, it is normally with a taper. So best example I can quote here. So spindle in lathe machine. Spindle in lathe machine. So where you are going to change the speed with the stepped cone pulley. Okay, so normally it has some taper. That's 1:100, 1:100. Okay, so next one is a counter shaft. This is a secondary shaft. This is what a secondary shaft. Counter means so to balance. Okay, so now these are normally used to get the same rotation of the driver and driven. Normally these are used to get the same rotation of the driver and driven. Okay, so suppose if you want to get driver rotation also as a clockwise and driven rotation also as a clockwise, then you need to go for a counter shaft. Okay, you need to go for a counter shaft. So now normally this is used to maintain same rotation direction or same rotation direction between driver and driven. Okay, next one is what is jack shaft. Okay, so now this is used to the again it is almost all similar to the counter shaft. Okay, it is similar to the counter shaft. Okay, but this the thing is that it is going to place it in auxiliary or intermediate. Okay, auxiliary or intermediate. Okay, so now counter shaft may consist of the gears. Okay, gears. Okay, so this is also same application, jack shaft. Okay, right. So next line shaft is what it is large length here. It is of large length, so where you are going to connect number of shafts in a line with the help of couplings. So now the line shafts are there in large workshops where you need to transmit the power on a single shaft. Okay, so this is what large shaft. Okay, so which is connected with the help of couplings. Okay, with the help of couplings. Okay, now this is all about the theoretical portion of shaft. Okay, now so the shaft design on a strength basis. Okay, shaft design on strength basis. No, you have a two parameters here for design of shafts. One is what a strength, another one is a rigidity. One is strength, another one is rigidity. Okay, so how you are going to say strength? Strength is what a capacity, or it is in a resistance of a component, so which can sustain. So before go to make an fracture here. Okay, that is what in terms of stress you are saying it. Okay, so now if you consider the torsional shear stress relations. Okay, now we'll go for torsional shear stress relations. Torsional shear stress relations. So let us notify here. Okay, T by J equal to G theta by L. Okay, this is equal to what? Tau by R. Okay, tau by R. Now, if a shaft is purely subjected to the torsion, okay, if it is subjected to purely torsion, so you can use only one relation. Okay, if the shaft is subjected to multiple loads, that is what power transmission as well as was subjected to some bending moment. Okay, or a bending stress, then again you need to go for consideration of some more formulas. Okay, now let us look out here. The relation which is there, tau by R to T by J, which stands for design based on strength. Design based on strength. Okay, now the relation, so which is there, G theta by L equal to T by J, which stands for design based on rigidity here. Design based on rigidity. Clear? Suppose if they say so design the shaft based on strength basis, then you go for this relation. Suppose if the design is to based on rigidity criteria, then you go for this relation. Okay. So how you are going to get the dimensions here? So you are going to dimension with the help of this polar moment of inertia. So now J is what? It is a polar moment of inertia. Right? This is what? Pi d to power of 4 divided by 32. So here also same. J is what? Polar moment of inertia. So now this is what? Pi d to the power of 4 divided by 32. Right? Now look out. So you are going to get some standard equations here. If you want to find out the diameter of the shaft, if the stress is given, okay? So now this is what? A T d equal to 16t divided by pi into tau. This is what? Cube root. This is what? Cube root. Okay. So now in this case, T is what? The torque transmitted by shaft. Okay. So tau is the allowable shear stress of shaft material. Shear stress of shaft material. Okay. Now, so if you know the torque and if you know the tau, you can directly calculate the diameter of the shaft. Okay. So for this one, you can refer the design data handbook. That is what? Chapter number 3. Okay. So refer design data handbook. So chapter number 3 here. Okay. Chapter number 3. That is what? Design of shafts. Design of shafts. Okay. So now let us look out here. Okay, now this is what? Design of shaft. So here you can just check out. C is the distance from neutral axis to the outermost fiber. D is diameter of solid shaft. Okay. So now table number 3.5, it recommends to the size, standard size available in market. Okay. So next is what? J equal to polar moment of inertia of cross sectional area about axis of rotation. Okay. Next, ratio of inside to outside diameter. That is what? Capital K. Capital L is length of shaft in mm. M, capital M is bending moment. Okay, that is what? Newton mm. Small n is speed of the shaft. Okay. Capital P is power. Now T is what? Torsional moment. Now here you got a different notations here. Sigma B stands for stress due to bending. Okay. Sigma D stands for design stress, allowable stress, permissible stress. Right? Sigma D, it is what? Allowable stress, permissible stress, or design stress. So sigma E stands for stress at the elastic limit. Stress at the elastic limit. Suppose if you want to design for elastic limit, then you go for sigma E. Tau is torsional shear stress. Tau D design shear stress. Tau E shear stress at the elastic limit. Omega is angular velocity radian per second. Theta is angle of twist per degree. Okay, angle of twist in degree. Okay. Now let us look at equations here. Now, suppose now all the equations are provided here with the consideration of hollow shaft. Consideration of hollow shaft. Okay. Now look at equation number 3.1. What it is there for solid shaft? Okay, 16t divided by pi dq. If you rewrite this equation, you can find out the diameter of the shaft. Okay. Now let us look out here. Okay. So if you substitute k equal to 0, what will get? 16t divided by pi tau d to the power of 1 by 3. Right? To the power of 1 by 3. Clear? Okay. Now, suppose if you want to find out the diameter of the solid shaft based on deflection, then you can use this equation. 584 TL divided by G due to power of 4 for solid shaft. Now it is what? In terms of degree. Theta has to be in terms of a degree. Then you can use this equation. Right? Next. Now, other considerations you need to take care here. The thing is that the value of CM and CT. Value of CM and CT. Okay. So now value of CM and CT are used if you want to design the shaft based on ASME code. Based on ASME code. So suppose if you want to design an axle, so where a stationary shaft is there, the shaft does not have any rotations. It requires only for supporting purpose. Then you can go for calculation. Using the CM equal to 1 for gradually applied load, CM equal to 1.5 to 2 for suddenly applied load. So here also same. Okay. You will know what is the meaning of CM and what is the meaning of CT. Suppose at the time of designing the shaft based on the ASME code. Next is steady or gradually applied loads. It is of 1.5 for bending, okay, and 1 for torsion. Okay. You'll just look out subjected to minor shock loads. You can select 1.5 to 2, 1 to 1.5, right? Suppose if they are not provided what material, then you can refer these materials. That is what properties of shafting materials. Commercial cold roll shaft, okay, elastic limit 241, tension 241, compression 122, it is a shear. So the percentage of elongation is 35. Hot rolled or forged steels, okay, so 3.5% is nickel, okay, and chrome vanadium shafts. Okay? You can just refer any one value here. Okay? If they are not specified what type of material you need to use, then you assume the type of material and notify the elastic limit. Then you consider suitable factor of safety. Then you use the design stress. Okay? Now this is all related to fatigue. Now you just look at table number 3.5 here. This is the standard shaft sizes in mm. Now 6 mm diameter, 8 mm diameter, 10 mm diameter, 12 mm diameter, 14, 16, 18, 20, like that. Okay. Next, maximum permissible working stress for shafts. Suppose if it is simple bending, okay, you can go for 83, 110, again based on the type of material here. Okay. Next, allowable bearing pressure. So you need this bearing pressure at the design of journal bearing. Okay. Now let us put. Now these are the important tables. Okay. Table number 3.5. Okay. Then table number 3.3. Then table number 3.1. Okay. Now the equations which are required to design a shaft when it is subjected to combined load, that is what when it is subjected to shear stress as well as bending stress. Okay. Now you need to go for two theories of a failure shear. One is maximum normal stress theory, another one is maximum shear stress theory. If the material is made of ductile, then you go for maximum shear stress theory. If it is the material is made of brittle, then you go for maximum normal stress theory. Okay. Now this is what based on simple here. This is what simple. Okay. Now D naught equal to 16 divided by pi sigma max. That is what allowable stress or design stress. Okay. M plus root of m square plus t square. Okay. Now if it is a hollow shaft, you substitute value. Suppose if you want to design for the solid shaft, okay, then you just observe it. So substitute k equal to 0 and d naught equal to d in the above equation for solid shafts. If you substitute k equal to 0, you are going to get the diameter of the solid shaft. Okay. Now this is what based on the simple theories. Okay. Now suppose if you want to design the shaft based on the ASME code here. ASME code. Now according to maximum normal stress theory, 16 divided by pi sigma max. Okay. 16 divided by pi now. Okay. Pi tau max. Suppose if it is subjected to fluctuating loads. If it is subjected to fluctuating loads, so now you need to find out the value of KT. Value of KT. Again referring the stress. Let us see what is the KT from index table. Index. KT is not there. Okay. Okay, so we need to find out what is the KT. Okay, whether they are specified KT equal to what? No. Specified KT? No. So KT is it is a stress concentration factor. KT is stress concentration factor. Okay. Now the important equations you need to remember. Okay. So now normal design, you refer equation number 3.5a, 3.5b. For ASME code 3.6a, 3.6b. For fluctuating loads based on the maximum normal stress theory, it is 3.7, 3.7b and 3.7c. Okay. So now this is what if it is a slenderness ratio is there. Okay. If it is slenderness ratio is there, then you go for this equation. Okay. Okay. Now we'll come back to the theory portion here. So now the equations are you refer chapter number 3, you have all equations here. Okay. Now suppose how to calculate the bending moment. Now in this case you need to calculate bending moment. Okay, once you calculate the maximum bending moment, so use that maximum bending moment to find out the maximum bending stress. Otherwise you may get the wrong answers. Otherwise you can get the wrong answers. Okay, so now regarding ASME design code. Okay, so you need to find out some equivalent torsional moment and some equivalent bending moment. Okay, so before that one it's better to go for one problem here. So I'll solve one problem. Okay, so okay.